Good afternoon, guys. It's Friday afternoon, and I'm going to try to get a couple more lectures up today, early tomorrow morning. Anyway, today I want to discuss the spin-orbit interaction. Most often, it's coined the spin-orbit coupling. And so it's a rather interesting reaction. So what happens is the following. Again, I think you want to look at the figures in your textbook while I'm going through this lecture. It is a coupling between the orbital spin and the intrinsic electron spin. Now it's kind of it's a little complicated how it comes about, and so it only manifests itself when L is not equal to 0. So clearly from here, then, if L is not equal to 0, then M sub L has values of negative L plus 1 through 0, L minus 1 to plus L. Okay, so when L is equal to 0, then M sub L is equal to 0, and then there's no orbital magnetic moment and no orbital angular momentum, right? So if L is equal to 0, there's no orbital angular momentum. Okay, so it's for states where L is not equal to 0. And so the way this comes about, if we go back to a Bohr model argument. So here is the nucleus. Let's deal with the hydrogen atom since it's the cleanest of the models. So this is going to be plus E, right? One proton. And around it we have an electron in orbit. We know that this gives rise to an orbital angular momentum. Okay, and also the electron now has an intrinsic spin angular momentum. And it's probably best here in this case to think about this in terms of the electron's reference frame. So here's the electron. And so instead of looking at the nucleus at the center, where we're looking at the nucleus, in this case the proton, which is in orbit around the electron. This actually constitutes a current. This constitutes a current, which then is going to generate a magnetic field at the electron. Generate a magnetic field at the electron. And so what we're going to have here then is a magnetic field where the electron is. The electron is going to react, quote unquote, or interact with the spin magnetic, the electron spin. And so here we are in the reference frame of the electron. And so what happens in this case is we're going to have a magnetic interaction between the electron spin and the field generated by the nucleus now, which is in orbit about the electron. Okay, so the bottom line is that neither L nor S are good quantum numbers. And what happens then is that one looks at the total angular momentum we call that J, and that's going to be given by the vector sum of L, the orbital angular momentum, plus S, the intrinsic spin angular momentum. And we're working with angular momentum here, and so then by analogy, the magnitude of the total angular momentum now is going to be the square root of J times J plus 1 times h bar. And Jz is going to be then m sub j times h bar, where m sub j is going to be equal to negative j plus 1, all the way through 0, j minus 1, plus j, much like in orbital angular momentum and in intrinsic angular momentum. So now the permissible values of j are going to be then, j is going to be equal to L plus S, L plus S minus 1. It'll go through 0. 0, as you're going to turn out, is not an option. And then this is going to be down to the magnitude of L minus S. So these are going to be the permissible values of J. For instance, if we look at an example here for an electron, with S equals 1/2, for instance, and L equals 1, then the permissible values of J are going to be then L plus S, all the way down to the absolute value of L minus S in increments of 1. And so this is going to be 3/2 and 1/2. So those are the permissible values of J for L equals 1 and S equals 1/2. For example, if S is equal to 1/2 and L is equal to 2, then the permissible values of J are going to be then plus 5 halves, plus 3 halves, plus 1 half, negative 1 half, negative 3 halves, and negative 5 halves. I'm sorry. This is a mistake. Let me get rid of all these. Sorry. There we go. Now we're good. Okay. 5 halves, 3 halves, and 1 half. Okay. So those are the permissible values of J, and you can go on and on with other quantum numbers. Okay. So we can invoke. We can invoke the vector model that we've used previously. And so if we look at the vector model, and if this is L, and then this is S, then this is going to be J, and likewise, if this is L, this is S, and then this would be J. And again, this would be J is equal to L minus S, and this would be J is equal to L plus S, and then this is for an S equals 1/2 single electron system. Okay, so we can continue with the vector model, and so if we were to look at the J equals 3/2 state, again we would have four vectors of magnitude J. Again, remember this is going to be for L equals 1 and for S equals 1/2 as our example. So the magnitude of J is going to be the square root of 3/2 times 3/2 plus 1 times h bar. And so that's going to be then 5/2 times 3/2, which is going to be the square root of 15/4 h bar. If we look at the projections along the z-axis, the z components of the total angular momentum, then we're going to have negative 3/2 h bar. We'll have negative 1/2 h bar. We'll have plus 1/2 h bar. And we'll have plus 3/2 h bar. And these are the values of Jz, the z component of the angular momentum. Remember now that Jz is going to be equal to m sub j times h bar, where m sub j now is going to be equal to j minus 1, blah, blah, blah. This would be negative j plus 1 and negative j. Okay, those would be the ranges on m sub j. So I want you to recognize a couple of things here, that the m sub j values are always even. M sub j values are always even. And m sub j then is going to be either 2L or 2L plus 2. So there's a notation here. There's a notation here that I want you to appreciate, and it's called a spectroscopic notation. Spectroscopic notation. And it's best to describe this notation in terms of looking at, again, the hydrogen atom. So we'll go down to this page. And so then here is the ground state. Here's n equals 1, L equals 0. And so we have an electron in the ground state. And so J then is going to be L plus S, L plus S, which is then going to be 0 plus 1/2, which is 1/2. L equals 0 corresponds to an S orbital, and we use capital S in this notation. And so then the ground state is going to be a capital S. It's n equals 1, so there's a 1 out in front here. And then this is 1/2, where that's the total angular momentum. Okay, so this comes from n equals 1. This is the orbital angular momentum. And this is the total angular momentum. Okay? So now if we look at the 2p state, right? So this was the 1s state. If we look at n equals 2, L equals 1, which is the 2p state, and then what happens there? So so now what we have is we have n equals 2. L is equal to 1. Okay, so an electron in this state can have a total angular momentum of L plus S to L minus S, which means that this is going to be then 3/2 and 1/2. So then this state's going to split. Again, this is going to give rise, right? This is going to give rise to m sub j's, okay, which will give rise to a magnetic moment, which will interact with the magnetic field generated at the electron from the nucleus. And so then this is going to split now. Oops. Going to split into a 2p 1/2 state and a 2p 3/2 state. Okay. And again, bearing in mind, let's just scroll down a little bit, right? So this is going to be p, 2p 3/2, 2p 1/2. Again, this comes from n is equal to 2. This comes from L is equal to 1. L is equal to 1. And then this is the total angular momentum. J is equal to 3/2. So this is the orbital angular momentum. This is the total angular momentum. And the same here, right? So this is going to be the orbital piece, and then this will be the total angular momentum. orbital angular momentum. So if one were to look at the transitions now, the energies here, right? The energies here, whether this is an emission or absorption, right? Remember these energies are on the order of 10 electron volts. The splitting between these levels is on the order of 10 to the negative 5 electron volts. So my scale here is not right? This is a very small splitting, but spectroscopically can still be seen, and that lets you know how good these spectroscopists were at that time. So again, if we were to look at the directions of momenta vectors, this is going to be L. In this state, this will be the direction of L. Okay, this is going to be the direction of S, and then this would be direction of mu sub S, and then this would be the direction of S. This would be the direction of mu sub S. And in both cases, B is going to be in this direction as well. So you see that the low energy state, which is not at all surprising, is when mu sub S is aligned with B. The high energy state is where mu sub S is anti-parallel to B. And in terms of angular momentum, the high energy state is where L and S are in the same direction. Low energy state is where L and S is in the anti-parallel direction. So I know that's complicated. Again, this comes from figure 9.11 in your text. You should be concentrating on figures 9.10 and figure 9.11. Study hard, because there's a lot of stuff going on there. So I want you to also study example 9.4, which is another really fine example of the spin-orbit coupling interaction in what is called the sodium D-line doublet. Okay, and so definitely study that. Alrighty, well, that's what we have for this segment. I'm going to pick this up with exchange symmetry, and we'll keep on pushing on. Two more sections, and we're done this chapter, people. And this is last couple of chapters are just so important that it really warrants some some good attention. Alrighty, take care. Bye.